Boom.
Someone have a question? You on the right side. I will do it on the left side.
And I will go to people with questions.
Okay, can you hear me? I'm not sure. Yep. Hi everyone. I think I'm starting. We are just 10 minutes late, and I think that most people who are interested are here. I hope you like the problems. First of all, congratulations. We are very happy that I think all teams solved 2 problems. Congratulations. I don't think that the easiest problem here was hard enough that no LLM could solve it. So congratulations, you're still much better than the best LLMs around. Round of applause for you, please. Okay, after this applause to humans, we can move on. These are all the judges that were to give you these problems. I'm Federico, and everyone else is on the first row there. Only one is missing. Thomas, you couldn't come. We hope you like the problems. We worked on them for some months. And in the end, we are quite happy with the final result. So, some statistics about the contest. I currently don't know how the end of anything that happened post-freeze. So what I'm giving you is no spoiler whatsoever. I just don't know anything more than you. Nothing incredible here. I would say that the most incredible thing is the fact that problem A was the first one solved, while we thought that maybe it was the 4th easiest or something like that. But I guess that its position in the scoreboard made it so. And congratulations, because then after it was solved, many teams solved it, much more than I would have expected. And then apart from that, I would say that it more or less went as we would have expected. Maybe we would have expected more solution on I, and we were very surprised by the fact that Scuola Normale Superiore could solve E somewhat early in the contest. That was for us one of the hardest problems. Apart from that, I mean, languages are, as always, C++ plus epsilon, so there is not much to say. Now we'll go through all the problems, starting from the one with most solutions before freeze, going until the one with least solution before freeze. These are solution sketches. They will not contain all details. Online, you can already find the editorial if you want the details of the proof. For the easy problems, we'll go much faster, in particular because everyone solved all of them, and then we will start to be a bit more careful. So, first problem, this is a problem of mine. This was meant to be the easiest problem in the contest, and I think it was solved by everyone. It's not meant to be a particularly easy problem, but it was too easy for you, it seems. So the problem reads like this. You are given n strings that you want to have as subsequences, and another string, which is t, that you don't want to have as a subsequence. And then you want to construct a string with this property if it exists. Okay, if the forbidden string is a subsequence of the desired subsequences, then the answer is no. And otherwise, you can make a greedy construction that if I thought that one team didn't solve it, I would go through it. But since all teams solved it and we don't have infinite time, I will just show you what's the idea. So S1, S2, and S3 are the strings that you want as subsequences, and T is the string that you don't want. So the idea is that you start to add letters from the strings that you want, and you try to avoid adding letters from the string you don't want. So here, you add an A. Then you can add a B, for example, and this does not change how much of T you have as a subsequence. Then here you can add another A, and this is improving everything else. But now you cannot improve your situation with S1, S2, S3 without adding a C, so you add a C. And you proceed in this way, but of course adding a C makes it a bit more, there is a bit more T inside your final answer. And you proceed like this until the end. And if you are able to finish before finishing T, the answer is yes, and otherwise the answer is no. I don't want to enter into more details because everyone solved this problem. So this is the solution. There was just a minor thing to take care of. I think that some of you got TLE because there's a catch. But apart from that, this is everything. And we move to the second problem. Andrea? There's another one. Okay. Does this work? I don't know if it works. Does this work? Maybe. Okay, second, well, actually, the other problem that got, that everybody solved within the freeze is the ultimate wine tasting event. And first solved by Masaryk University after 30 minutes, which is quite impressive, especially because I think we overestimated the difficulty of this problem. We thought it was harder than it appeared. So the problem is about, well, go quickly because we solved it. There are two n wines arranged in a line, n white and red, and you have to form two subsequences with them, each of n wines, and then swap the first two elements, then the second two elements, up to the last n. And the goal is to get all the white wines on the left and the red wines on the right. Can you do it? Yes, no. So this problem invited perhaps a greedy solution. That, however, is wrong. Like playing greedy solutions don't work, and hopefully the samples were enough to catch it. The actual solution, I mean, the cleanest one is to find an equivalent condition, and then you verify this condition, and that's trivial. So what is the condition? Well, let's start by assuming that this splitting into subsequences exists. Let's call them A1, AN, B1, BN. And, well, I'll go quickly even here because basically the idea is that you make a few observations and, well, I skipped this. All right, here. What you can conclude is that the first half has to have an even number of white wines, let's call it 2H, and half of these, so the first H, have to be a prefix of the string. And then you can make the symmetric of this, of course, and so the last n wines need to have 2H red wines, and the last H are red. And this is also a sufficient condition. Exercise, I mean, you solved it, but okay. Yeah, and that's it. And you can obviously verify this in linear time. Okay, and then the next one is also me. It's odds, which we thought was easier than the one before. Was solved by all the teams but two before the freeze.
first solved by École Polytechnique Fédérale de Lausanne after a bit more than half an hour. So this problem is a bit, I mean, the statement is quite simple. Still, you have a streaming platform where you need to watch n videos of given durations. And then you are obviously shown some ads in between videos. And you're shown an ad either after 3 videos, 3 consecutive videos, or after at least k minutes since the last ad. You can choose the order in which you watch the n videos. What is the minimum number of ads that you can be shown? So basically what happens here is that the ads will form some groups of sizes 1, 2, or 3, and you want to minimize the number of groups. So this is in fact a greedy problem, a greedy solution, where what you can observe is that the long videos, which are the ones that last at least k minutes, or seconds, minutes, will necessarily go into different groups. So let's lay them out and form some groups with these long videos. And then we need to put the other ones. So the convenient thing is to try to form as many groups of 3 videos as possible by pairing up the short videos and assigning them to one of the groups. And you can do this as long as you find pairs that have a total duration of less than k minutes. So you try to do that, you go on as long as you can, and then you are left with some short videos, maybe some long videos, and first you pair them up as much as you can, and form groups of size 2, and everything that is left are groups of size 1. And the complexity of this is n log n, because you have to sort to do step 3, and then everything is linear. All right?
Hello. I'm the author of problem A. There is some meme here. Do you have anything stronger? It's an election year. This is the fourth problem from the difficulty, but it was the first problem to be solved. I guess because it was conveniently on position A. So if easy problem is there, someone will solve it even if it's not the easiest problem. We had 43 solved submissions here. What about this problem? So we have an election, and each vote in this election is a ranked list of candidates, like a permutation of candidates, how much people prefer different candidates. And you also have some claims that candidate A should be more preferred to candidate B. More than half voters should select candidate A over candidate B, and vice versa. And you need to select a list of votes which would make it happen. So as some small, okay, I don't have a small example, but the answer is always yes. But let me maybe tell you where this problem came from. There is a thing which is known as Condorcet paradox, which is you can design elections in the following way, that it's not possible to select the winner, essentially. And this is exactly what is a second example in this problem. Like, if you design your voters carefully, you can have that candidate 1 is better than candidate 2, but candidate 2 is better than candidate 3, and then candidate 3 is better than candidate 1. So in a way, you cannot stop anywhere in this cycle, because wherever you stop, more than half people will prefer to change, which I think is a funny subject. And actually, this problem extends this topic in a way that you are asked to not just make a cycle of length 3, but any graph, any graph which is possible, and you can always do it. And how to do it? Let me denote like delta AB of voters is how many votes prefer A to B minus how many votes prefer B to A. So essentially, I want to find some votes such that delta of Z votes is larger than 0 for every required edge. So if I want candidate A to be better than candidate B, I want this delta to be larger than 0. And how do I do that? I actually I zoom in on every edge individually, and I construct 2 votes just for that edge. And they'll have some properties which essentially mean that delta of the edge I'm caring about is larger than 0, and delta for any other pair of candidates is 0, so they're not touched. So maybe let's see for this pair of votes, if I want to make sure that my candidate 1 is larger than candidate 2, so candidate 1 beats candidate 2, let me add those votes. You will see that in both of those votes, candidate 1 beats candidate 2, but for any other pair of candidates, they're not changed, right? So for example, if I would look at candidate 1 and candidate 3, in the first vote, candidate 1 is better than candidate 3, but in the second vote, candidate 3 is better than 1. So kind of the balance does not change for any other pair of candidates except for the specific edge I chose to care about. And let me just kind of do those votes for every edge, and then I get 2 times n choose 2 votes, which is about n square voters, which is way less than we allow. That's it. I guess the next problem will be problem B, urban planning by Petr Mitrichev.
Hello, everyone. So problem B was about creating a grid with exactly given the number of rectangles. So note that actually the constraint is very precise. So if you fill the entire grid with sharps, you still have only a bit more than 4 times 10 to the power of 12 rectangles. And even despite this, when we were looking at submissions during the contest, almost all teams have different solutions. So there are so many different approaches here, and what I will explain is just one possible, and probably it's not even the simplest one. So the idea we have is, let's just approach K gradually. So we have several connected components. First we make a large one, we get almost K, and then we kind of correct by adding a few more. So what we do is we start with a 1 times 2025 rectangle, and then we add cells one by one, like this. So we go row by row and go from left to right. And every time we add a new cell in row R and column C, we get R times C new rectangles. And we will reach the maximum possible rectangles within less than 2,000 rows. And then since every time we add at most n squared rectangles, we will get as close to K, except for at most n squared, or in this case 4 million rectangles. So now we need, with the remaining connected components, to cover just 4 million rectangles, and that's much easier. But we can actually do the same. So we can skip 1 row and then do the same process. And then we will be done after 7 more blocks, actually. So some more thoughts. Actually, the online mirror, this was the only problem that was different in the online mirror, and there the constraints are larger. So you have to get even closer to the maximum possible number. So you can try thinking about it yourself, or you can check out the editorial for online mirror, which is already public at Codeforces. Right, so there's a hint. And another point that actually the we were talking about rectangles which have a boundary of sharps, but we didn't say that we must have also parks inside the rectangle. Actually, all solutions we know don't depend on this. They also have parks inside the rectangle as well. So the idea was that if some team tries to implement some hill climbing solution, then it will be harder for them because counting such rectangles is harder. It requires n squared log n to the best of our knowledge. Yeah, that's it. And so the next presenter is Jovi. But I also need to make a short video for the ICPC quest. Just a moment. Congratulations to all winners. Thank you.
Okay, so hope you can hear me. This was problem H, Stadius. So we are getting into the medium difficulty problems, I would say. It took a while for the first team to solve Stadius. So the question here is, you are given, you need to arrange Stadius on a 2-dimensional grid, in a 2-dimensional city. You are given the location of the first and the last statue, and you are given the Manhattan distance between each consecutive pair of statues, and you need to complete the arrangement if it is possible. Okay, so to start, let's also give a name to the distance between the first and the last statue, which we know since it is given. And then the key insight is that we have two conditions that together are necessary and sufficient for a valid arrangement to exist. So first, the sum of all the distances needs to be even, and second, each distance has to be at most the sum of all the other distances. And this is because all these numbers that we are looking at, they need to form the side lengths of a polygon. Okay, and so well, condition 1 is easy to check for the Manhattan distance, and condition 2 is the triangle inequality applied at every possible edge. Okay, so we have necessary conditions. Let's see the harder part, which is to construct an actual arrangement, assuming that the two conditions actually hold. And we do it inductively. So we, well, okay, if there are two statues, we already have them, so nothing to do. If we need to place at least one new statue, so n is at least 3, let's call S1 through Sn the locations of the statues. What we want to do, it's an inductive construction, so we want to place the statue n-1 in such a way that, well, first, it needs to be at the correct distance from the last statue. Okay? And second, we want the two conditions to keep being verified in order to continue our inductive process. So if we call d0 hat the distance between statue 1 and statue n-1, we want d0 hat through d-2 to satisfy our two conditions 1 and 2. Okay, so let's see a picture. We have first and last statue. As I tried to convince you, we now want to place the statue n-1. Okay, so we can place it. We have to place it at distance dn-1 from the last statue. So the locations that we can pick from form a square, as in the picture. And the only thing that we really care now is what's the value of d0 hat. Okay, so what's going to be the distance between statue 1 and statue n-1, which we are now placing. Okay, and if we look at it, if we make statue n-1 go through all possible locations, the corresponding values of d0 hat, they fill an entire range between the values that you see there, d0 minus dn-1 absolute value and d0 plus dn-1. Okay, they fill all this range, but actually only every other value because the parity has to stay fixed. Like in the example, you see that you get all the even numbers between 6 and 14 as possible distances. Okay. Now, the parity of all these values of d0 hat is exactly the parity that we need to ensure condition 1, so that's sort of automatically satisfied. What we need to do is to pick a value of d0 hat so that condition 2 keeps being satisfied. So the triangle inequality is still satisfied. You might have several possible choices that can work. Okay, the choice that came to mind for me was to pick the minimum between those two numbers. Okay, and the idea is that d0 plus dn-1 is the largest possible that you can do, and maybe that one works, but it might happen that it violates the triangle inequality, and so you decrease until you reach the first value that can work, which is d1 plus ... plus dn-2. Okay. Once you have this claim, which you can come up by thinking a little bit about the problem, you can actually prove very easily that this actually satisfies condition 2 by just distinguishing the two cases. So in the end, you have decided a suitable value of the 0 hat. You just need to find the actual location of the n-1 statue, and that you can do in constant time. So overall, we have a linear time solution inductively to build all the statues. Okay, and now we have Pedro, I believe, for problem E. Is that plausible? Yes.
All right. I know everyone's tired and you want to know the results and get some food, so I'll try to be brief. So I was the author of problem E, and this was intended to be one of the hardest problems. We were very happy to see 2 accepted solutions before the freeze. So let me tell you just very quickly what the summary of the problem was. So you're given a graph, and this is kind of a game between 2 agents. One of them was the supporters club of a soccer team, because of course we're in Portugal, so the problem has to be about soccer. So the supporters club needed to go from node 1 to node n, and they wanted to minimize the number of roads that they're taking to do so. And then an adversary, in this case the police, knows the movements of this agent, and they can at any point and exactly once remove one of the edges of the graph. And the goal is to compute the minimum time required for the agent to reach n if they both play optimally. I'll tell you a funny story, which is the reason why I came up with this statement was because my cousin is a big Benfica fan, and we actually went to a game, and he was coming back, and the police blocked one of the roads, so he had to go around and took like twice as long to get home, and he was complaining about that, and that's how I came up with this statement. Okay, so now let me tell you a little bit about the solution. So I'm going to start by just introducing some very quick notation. We're going to call f of v the minimum number of roads needed to reach n from v. So that means that the f of 1 is the answer. It's the result you need to compute. And f of n is 0, since if you're at the nth location, the distance is 0. And so let's suppose that we're in a situation where no road has been blocked, and the supporters are in some node v. So in this case, the police can do one of 2 things. Either block one of the roads adjacent to v, or let the supporters pick some road to keep going on their journey. And notice that in the first case, blocking one of the roads. So let's denote by VE the shortest path from V to N with edge E blocked. So if you pick some edge to block, G of VE is the shortest path from V to N with that edge blocked. And G of V is the max over all edges that are adjacent to V. So this means that in the first case, the police might as well pick the edge that maximizes this path. Since if they pick this edge, this is going G of V is exactly the path that the supporters club will take to get to the destination. So this is one of the options. And the second option, if they let the supporters club go, they will pick the vertex that minimizes f of u. So they'll pick the cost will be 1 plus the minimum over all the f of u's, where u's are the vertices adjacent to v, since they might as well pick whatever vertex minimizes the distance in terms of f. Okay, so now we have to compute f of v and g of v, and we can first observe this this equality, which basically spans from the previous slide, where f of v is equal to the max between g of v, which corresponds to the police blocking one of the roads adjacent to v, and 1 plus minimum of u v f of u, which corresponds to the supporters club picking one of the edges adjacent to v. So this is the first observation you need, and now the key part of the problem is how do you compute g and then f. So I'm going to start by assuming that we already know g and just show you how to compute f, and then I'll show you how to compute g. So to compute f assuming g, this is actually the solution is actually very similar to Dijkstra's algorithm. We can use a greedy algorithm very similar to Dijkstra's, and so the correctness of this algorithm follows from the same idea of Dijkstra's algorithm. So if you set an array of f's where initially f of n is equal to 0, and initially you only consider the vertex n to be processed. Basically at each point you want to pick the unprocessed vertex v with lowest value of f of v, and you want to mark it as processed, just like you do in Dijkstra's algorithm. But in Dijkstra's algorithm, you process it by kind of looking at the adjacent vertices and updating their distances. Here, instead of updating distances, you basically apply the formula from the previous slide. So you set f of v to be equal to the max of gv and the minimum 1 plus f of u, assuming that for all the u's that are adjacent to v. So the intuition is that you're applying the formula of f one pair of adjacent vertices at a time. And so this is what you're doing, and the same thing happens in Dijkstra's algorithm. And the key observation is exactly because of the correctness of Dijkstra's algorithm. At the end, f of v is equal to this array actually computes the values of f of v. And the key idea is that when we pick the lowest f of v, all the remaining vertices have higher f of v, so we'll never update this formula using an f that is larger than the current one. And so you might as well consider this f the actual value, the actual maximum value you can get to. Okay, so now let's compute g. Computing g was actually the hardest part of the problem. So once you compute, before you compute f, you have to compute this g, and recall that g is, I give you, for a certain vertex, what is the shortest path from v to n that blocks one of the edges adjacent to that vertex v. So to do this, we're going to first consider the BFS tree that spans from n. And then the observation that you have to make is that g of v corresponds to the following. It's some path that you start at v, you go down the subtree, so this BFS subtree that spans from n, some number of steps, potentially 0 steps. You hit some vertex u, and then you take one non-tree edge that goes to outside of v subtree, just like in the picture below on the screen. And then you take the shortest path from that vertex to n. The last step, number 4, you can just pre-compute, since you just can compute the BFS from n. But then the second 2 steps, computing the best optimal vertex to route through, is the kind of the hardest part. And there's multiple solutions. I know, like, some of the teams that got accepted solutions today have different solutions. So if you have a different solution from mine and you want to tell me about it, please do after the closing ceremony. So to find find the optimal u, basically one possible solution is you want to find all the valid paths from each v to all the possible u's. And you're going to do this basically recursively by computing all the distances to all the children of v. And you want to basically keep all of these values in a set, and each set will contain a pair of distance and the vertex u that we're routing to through a non-tree edge. And to do this efficiently, basically for every vertex, once we computed the sets that correspond to its children, we're going to merge all of them by picking all of them and adding 1 to their distances, which corresponds to taking one more tree edge. And now once we have this, the final thing we have to do is that if the minimum elements in the set will correspond to the best vertex to route through, but this vertex might still be going through a vertex in the subtree of v. If that's the case, we remove it, and then the remaining minimum elements in the set will give us the value of g of v. So the very, very final thing is, how do you merge these sets efficiently? We have to use union find to check if u is in a v subtree. And then finally, to merge these sets efficiently, we can use the small to large merging, which is the same algorithm using the rank by size of a union find to efficiently merge these sets. And then the total runtime of this is going to be n log m, log squared m, exactly because there's log m's. You need log m merges of sets, and then you also need log m to keep track of the sets themselves by inserting and removing. So that's the solution. And next problem will be presented by Igor.
So hello. Based on the stats, that was probably the most favorite problem of you all. So in this problem, we're given sequence of numbers, and we want to find some other sequence such that sequence A divide corresponding number in sequence B, all B's are distinct, and maximal is as small as possible. So our solution would be to build a graph and run max flow algorithm on it. So when the flow is n, we are okay. And so let's do some definitions. Suppose there is k different values in A. Now we will build a graph. Now we would want to add some other vertices to the other half of our graph. And we add vertices while, until we have a flow of n. That's a very nice solution, but the only problem is it works in this time complexity. And this is way too slow. Now we would maintain, we will not do this for each I. Instead, we will have some i's starting with all the different numbers that are present in the set, in our sequence. We will maintain for each number the set of indices that we are interested in. And then we always pick the smallest number not yet pretend that have non-empty set. We add all the edges, again with capacity 1. It's not shown here, but it should be with capacity 1 for each index in the set. And now there is actually that's the last step that many teams are missing to get accepted, that if we added this vertex with these edges and the flow increased, then okay, we will continue to try add numbers from this set. But otherwise, we would ignore all indices that are currently in the set MI, because they wouldn't help us. And we will only look at n plus cut distinct values of I, because we either add, have our flow getting bigger, or we remove some numbers from indices forever. So we have this time complexity, and it can be proven that E is this number, but we won't do it. And this is basically key points of this problem.
All right, we continue with the problem D, Morse code. This was attempted also quite a lot, 10 submissions before the freeze, and ultimately one accepted solution before the freeze by Karlsruhe Institute of Technology. So in this problem, we are given a set of character frequencies, and we are asked to determine a Morse code-like assignment where none of the codes are prefixes of each other, and where the expected transmission time for a character is as small as possible. So the first thought is that you can describe such an assignment using a binary tree in bits like this, which is the first sample case. So every edge is related to either a dot or a dash, and we place all the characters on leaves, and this ensures that we have no prefixes of each other. We also give every character some sort of depth based on how low I draw them, where a dash goes down 2 layers of depth, and this ensures that the depth of every character is equivalent to the length of the assigned Morse code sequence. So the first idea on how to actually construct such a tree is that if we know the shape of the tree, then we can assign which character goes where in a greedy way by putting the most common character as close to the root as possible. And up till now, this looks very similar to Huffman coding, which you may have heard of, but it is actually better if you have not heard of it, because attempting to do something different does not work and was a huge pitfall for a lot of teams. What we do instead is we look at some other optimizations. So if we want to know the shape of this tree, the exact shape initially is not that important, because if you have 2 vertices on the same level, then swapping those vertices and the subtrees below that does not change anything about expected transmission time. So the only thing we need to know is per level, how many leaves are there and how many internal vertices are there. So for this tree, this would look a bit like this, where on the left side I've counted the number of leaves, and on the right side I've counted the number of internal vertices. And this sequence of internal vertices and leaves can be constructed using a dynamic programming from bottom to top. So in order to accurately describe a state for what such a possible partial sequence looks like, we need 3 parameters. So firstly, we need to know what at our current level is the number of free vertices, where with 3 I mean that we have not yet decided whether we want this vertex to be a leaf or an internal vertex. We also have the same number for the next level, because making internal vertices affects 2 levels at once. And finally, we also want to know how many leaves we already have added so far. So we have 3 parameters. The value of our DP with these 3 parameters that describes the expected cost to that affects all edges that are below the current level. So the value that we're then looking after is the DP of 1, 0, n, because in the initial state we have 1 free vertex in the root, and nothing below that is determined yet, and we still need to place all n characters somewhere. One base case is that the DP of the empty suffix with no vertices and nothing to place is 0, because transmitting nothing costs nothing. There's also some boundary cases. If you do not have any internal vertices left, but you do have characters to be assigned, then that is obviously impossible. So in this case, we assign infinity. And there is also some other trivially suboptimal case. So if the number of internal vertices you have is larger than the number of remaining characters, then you already have done too much internal vertices and you could have done more efficient. So we also assign this infinity. So we don't do too much in our DP. And for all other cases, we will actually compute a transition function. And to determine the value for some DP cell, we have a minimum of 2 options. So either we decide that one of our free vertices will be a leaf. In this case, we reach our value from the DP of the VC minus 1, Vn, and A minus 1. So one less free vertex that has become a leaf, but also one less character to assign, which is of course only possible if we actually have free vertices remaining. And the other option is that we do not want any more leaves, so we decide to make all remaining free vertices internal vertices and go to the next level. So the VC number of internal vertices splits into something at the next level and something at the level after that, and we go down one more level. This incurs an additional cost of Fa, which is the sum of the A smallest frequencies, because the A smallest frequencies, which are in the subtree that we're computing, are now down one more level in this tree. So for all these frequencies, we need to have one longer code. So this is the other option in our DP. And together, this is enough to compute the answer for these, to compute these suffixes. So if you pre-compute this f, the value of the smallest prefixes, then this transition time becomes constant. And there were some requirements on the number of states. So overall, you can see that each parameter is bounded by 0 and n, even something better. So this is roughly a cubic number of states, which result in a cubic runtime for computing this dynamic programming table. And the final step is then to actually reconstruct the codes, which is a bit tricky, but not that hard. So you can just backtrack back through your DP and keep track of a set of partial codes for the current level and for the next level. So this concludes this problem. We continue with problem G.
So I was very happy because this problem was solved maybe just before the freeze or something like that. And I was hoping for something like that to happen, so that made me happy. So what's the problem about? I will not give a full solution, it would take too long. I will maybe give the main idea. So you are given the statement of the problem was talking about a national park, but you can think more or less of anything with different altitudes in different places. So imagine that you have an infinite grid and each cell has a number which represents the altitude, but these numbers are repeated periodically. So I'm giving you what are the numbers in an n by n part of the grid, and then you have to repeat this pattern everywhere. So now you have a full plane, a whole plane with altitudes, and the important thing about this altitude is that they tell you how long it takes you to move from one cell to an adjacent one according to this formula. Like if you are moving from a cell at altitude x to one with altitude y, then you pay 1, which is the time you would need to walk, and then x minus y in absolute value, if you have to climb or down climb. And then the question is, how many cells can you reach in a given number of seconds or steps, well, seconds? And the point is that if this number was 1,000, then you could just run Dijkstra, and this would not be maybe a very interesting problem. But the point is that I'm giving you a very large number for which most likely any optimized Dijkstra will not get accepted, and you have to understand a bit more. Like you have to understand what happens, like what's the shape you would expect. In some sense, you want to understand what's the shape of cells you would expect to be able to reach. And then the exact value of R most likely is not important. Like what's not said in the statement, that it's in some sense a very first observation, is that you don't care about counting the number exactly. In fact, we are not able to compute the number exactly. You just have to give us a very good approximation. Because at the boundary, lots of bad stuff can happen, but the claim is that this can happen only at the boundary, it becomes negligible when you go very far. Okay, and what's the main idea to solve the problem? The main idea is the following one. Imagine that you have a very long path, and along this very long path, since everything is repeated modulo n, at a certain point you will step on a cell that you have in some sense already visited. Well, not exactly the same cell, but its copy in a different pattern of the many patterns that you are copying to fill the whole plane. And this is the idea. Let's be more precise, since this is the main idea. So we say that a path is interesting if it is short, so its length is bounded by n square, and the initial and final cell are the same modulo n. This is what I want to say when I say that you have already stepped on a certain cell. Not exactly on that one, but on another one whose coordinates are equivalent modulo n. Okay, and the point is that if you have a very long path, you will for sure find one such interesting path along the way, and if you remove it, the sum of like the total length in this notion of length does not change, or at least it changes, but in the sense that the length of the initial path coincides with the length of the interesting path that you have removed and what remains. Let's see a picture. So we start with this path, which is maybe not very long, but it's long enough, and n is equal to 3, which means that the pattern, which is here identified by this square grid, is repeated every n steps. Okay, so you have this red path, and inside here, you may observe that you have found this subpath, which starts at 1, 0 and ends at 4, 3. And you may notice that 1 is equivalent to 4 modulo 3, and 0 is equivalent to 3 modulo 3. Okay, so this is an interesting path. I can remove it and collapse everything together, and that's exactly what I'm doing. So I remove it and I collapse stuff again, with the idea that I removed a path with a certain cost, and what remains plus the path I removed gives me the original cost. Okay, I do the same here. There will be another path that I consider interesting. I remove it, and now I end up with a very short remaining path. So in some sense, I prove to you, this is not really a proof, but it's an idea, that any path can be split in the sum of many interesting paths and then some cells that you don't really care about. And here it's where the fact that R is huge is important. Like, since the fact that you have these n squared cells will not play a role. Okay, but in some sense it is only going in one direction, and if you really want to convince yourself that this is a full solution, you would also need to prove the opposite, which I will just state without saying anything else. You also have to prove that if I give you a sum of interesting paths, then you can in fact concatenate them somehow. Maybe you add a bit of cells, but it will not be important, in order to create a single path. Both things are important if you want to show that the problem itself can be reduced to what I'll say in the next slide. So, what's the morals of the story that you should remember? That you don't care about paths, you just care about sums of interesting paths. And interesting paths are not that many, because they are short, and you will be able to find all of them. This is exactly what's going to happen now. So, what I'm describing here, it's a way, in some sense, to find the best interesting paths. So, an interesting path, it goes from, I may have a pointer. Yep. It goes from AB, which is the initial cell, into A plus IN, B plus JN. Remember that initial and final cell have to be equivalent modulo n. Okay, this is satisfied. I will iterate over all possible A and B, well, between 0 and n, because otherwise I would just get something periodic. And the same for I and j. Why do I have this bound on I and j? Because if you remember, for me, an interesting path is interesting only if it's shorter than n squared. And if I go into numbers larger than this, then I would get a path that is not interesting anymore because it's too long. Cool. And then for each chosen initial position and final position, I compute the minimum distance between the two. And I have to normalize stuff. This is maybe very hard to follow on slides, but if you want to have something that works, you'll have to divide by n. But forget about it for a moment. It's not important. And then I take also the minimum over all possible A and B. So Tij represents the minimum time that I need to move by In, Jn. Actually, since I divide it by n, Tij represents the amount of time that I need to move from a given cell, whatever cell, into another cell that is shifted by Ij. And in fact, this is how you should think of the problem. From now on, you forget about the original problem, and you believe me that the answer will be the same if you change the rules of the game. Now, you can jump from any cell by Ij, paying Tij, which is a value that we have computed, and you want to understand how many cells can you reach. But now, if you think a bit about the problem, now it has nothing anymore to do with shortest path, and now there will be some formulas. The formulas are, in fact, they look more complicated than they should, but it's just that I'm saying, okay, I want to compute the distance between the origin and a point. How do I compute this distance? I want to express the value, like the point AB, I want to express it as a sum of interesting paths, and then for each of them, I'm taking its cost, which is Tij. The formula looks complicated, but it's really not. And then once you have the formula, I am 100% sure that, in fact, more or less all teams here would be able to go from the formula to the final answer, which I will go through, which I will skip because there's maybe not enough time. But if you believe this formula, so if you believe the reduction, then you can more or less easily reduce it to computing a convex hull. So that formula, which is complicated, as you may know, when you have linear formulas, they often reduce to convex hulls. And in fact, this is one of those cases. It turns out that the answer itself is the area of a given polygon that depends on these numbers that we have computed here, times r squared. What is the moral of the story here? That the shape that you know a priori what is the shape of the reachable cells, and it's a convex polygon times how far can you go. And so it's a convex polygon scaled by r, so its area is scaled by r squared. Okay. It remains only one thing to do, which is in fact not that easy, or, I mean, it may still be a difficulty, which is how do I actually compute this Tij? Because I've told you that, okay, you iterate over AB, you iterate over Ij, and then you compute the minimum, you can compute a Dijkstra. But this most likely would not work because it would be too slow. How do you actually do it? If you do it the naive way, so you iterate over AB, over Ij, and you do Dijkstra, then this will have more or less, independently of the implementation you have, n to the 8 log n. This will get time limit exceeded for sure. Okay, then there are two optimizations. In fact, the first one should be enough. Like, it might be very hard to squeeze it in, but it could be possible. We were very, very lenient with the time limit. But otherwise, the second one is surely enough. So first of all, you don't actually need to iterate over all points A and B. There is just no reason to do that. Sorry, you iterate only over all points I and B, and then you use just one Dijkstra for all possible Ij, once you have fixed A and B. This is not a very deep idea, but you have already reduced the computation to n to the 6. Well, this, I could not squeeze it in, but I think it's doable. And then there is just one more observation to improve the complexity, and this one fits easily the time limit. And the idea is the following one. Well, first of all, Dijkstra, you can remove the log from Dijkstra, but let's ignore it for a moment. What you can really do is to observe that any interesting path, by its definition, goes through one special cell. And a special cell for me is a cell that has one coordinate equal to 0 or the other one equal to 0. And once you understand this, then since it goes through it and it's periodic, so it starts and finishes in the same place, you can actually assume that it starts there. You can actually care only about paths that are interesting and they start in one of these special cells. And since there are only O of n such initial cells instead of O of n squared, the complexity reduces and you get O to the n to the fifth. And I think that this was the solution that got accepted before the freeze. And finally, pinball.
Yes. Is it working? Yeah, great. Okay, so finally, problem I. Problem I of the contest had a brown balloon. I guess not many people saw that, but it was this brown balloon. I mean, not many people saw that because apparently not many people submitted it to the problem. So I guess you have to submit to the problem in order to get accepted. So if you don't submit, I guess there's no way that you can see the balloon of the problem. But it was brown and it was nice. And I'm sad that nobody got it. Although there were a few submissions after the freezing time, so I guess it's not all over. How do I? Okay. So the statement was that you are playing a game on an H by W grid with free cells, block type walls, and oblique walls. You have a small ball inside the grid, and you have to direct it towards the exit. How you do that is you first nudge it in one direction, you let it go through the grid, and at moments in time you can destroy the oblique walls. Now the first part of the solution, or like what you have to do, is you have to understand the structure of the problem. So in order to do that, we'll focus on the paths that the ball can take without destroying any walls. And if you do that on paper you'll realize that these sort of regions can be grouped, like the paths or like the way the ball moves can be grouped into regions, which some of them are linear, some of them are circular, depending on if there are block walls or not. And what happens when I destroy an oblique wall is that the ball travels basically from one region to a different region. This will make more sense if I go over to the next slide. And we see like the picture of the first sample case. So the idea is that these regions look like these, great, like these sort of colored lines. So like we have a red region, which is at the start, if we nudge the ball towards the left or the right direction. We have another blue region here, we have another green region, and we also have some other regions, which is like this purple one, or maybe this brown one, or maybe this cyan one. What we can do is we can think of it as a graph, where each vertex is a region, and the fact that we have oblique walls means that we can travel from one region to the next. So each oblique wall is in fact an edge between one region and the other. So here we've got a graph. What we can do with this graph, I mean, it makes sense to think about the minimum distance between one of the initial regions, so either the red one or the brown one, and one of the final regions, which in this example is just the green one. And if you compute that, you'll see that, so if you compute that, you see that there's like two mirrors. So it goes through two edges and you have to destroy two mirrors. And coincidentally or not, 2 is the answer to the sample case. So it might make sense to ask yourselves, is that the actual answer? It turns out it is. Okay, so it turns out that this is in fact the minimal number of mirrors that you need to destroy. We'll talk about it a little bit more here. So in order to prove yourselves that, you can just trust your intuition, but that won't help very much because you also have to do reconstruction. But the intuition here is that the distance described is a lower bound for the problem. Why is it a lower bound for the problem? It's because we are actually solving a different problem, which basically allows us to sort of bring back to life some already destroyed walls. So like if you think about what problem we are solving, in actuality, it would be the problem where after I destroy a wall, I can just spawn it back in. So like the relaxed problem would be choose k walls. For each time step, you can just decide arbitrary for any of the walls if they are active or not. And then it's like the matter of the ball reaching the end. That's actually an easier problem. So that's like the number of walls has to be at least the solution. So it's like a lower bound for the solution. Yes, actually, at most, but yeah. We can actually prove that any cell at a distance, any cell in a region that is at distance k can be reached. So like maybe it's not that clear in this picture. So for example, if I choose like this region of the blue one, I can reach that by first destroying the wall while the ball is traveling downwards. So I destroy this wall and I can get here. But if I do that, I won't be able to get here anymore. But I can get here independently by choosing a different time for which I destroy this wall. So the main idea is, technically speaking, I can get to any path that goes through these regions if I choose the timings of each of the walls in a perfect manner. Let's go back. But this is like not very trivial. I can give you a proof of that, but it will take time and we don't want that. What we can do is we can just construct it, and that's like an equivalent proof, and we're basically killing two birds with one stone because we already have to do reconstruction for this problem. How to do reconstruction? There are multiple ways. Some are easy, some are hard. I will describe perhaps the easiest one and the most elegant one. It's the idea of starting from the end. So why starting from the end? Because it gets this amazing, let's say, change to the problem where we're not destroying walls, but the walls are already destroyed and we can choose to restore walls. Why restoring walls? Because restoring walls is kind of converging towards the initial status of the problem. So that would be really easy. So what I'm trying to say here is the strategy is like this. Of course, starting from the end. If a ball hits a wall, if that wall would rather be destroyed, so we want the ball to go from, let's say, the kth region to the k-1th region, we suppose it was destroyed and we restore it. Now the ball is in the k-1 region and we can simulate it just as no walls would ever be destroyed. If not, we just continue simulating. So we just let the ball roll, as they say, and just let it be. So yeah, we simulate and simulate until the ball gets back to the starting point. At which point we actually have a solution for every wall, like the time of every wall where it should be destroyed. Yeah. Implementation is also a pretty important fact in this problem. Depending on the implementation that you choose, you can spend 45 minutes on solving this problem, or 3 hours and 45 minutes and not end up solving the problem. One thing that makes implementation easier, I can tell you, is if you sort of ignore the graph structure, or at least you don't try to build it explicitly as a graph, you just do sort of like 0, 1 BFS, where you have a state, and for each cell you have like the state is the cell and the direction, and you basically have cost 0 to go 1 step forward in that direction, like simulate 1 step forward, and you have cost 1 of jumping to the next region, which kind of accounts for destroying a wall and doing everything. And it's like 2 passes. One is a forward pass where you compute the distance for each state, and one is the backward pass in which you compute the reconstruction, just like all problems that require reconstruction and dynamic programming, I guess. So yeah, that was problem I think. Pedagogical? Maybe. Okay. I'll take that.
I don't really.
we have in the schedule we have 5:30. So let me see. Is Thomas Cerny around? Yeah. Are you going to do it with him or not? So. I can do whatever you wish. I think. Basically ready. I think we start.
Yes, and I will need to
I think we probably start with the request first.
Yeah, absolutely. And I can entertain a little bit, but we need sponsors. And that's a Huawei.
Let's see if I can.
So we can try to disconnect this guy.
Yeah. Nothing is on the screen now if we plug it in, right?
It will not be tested because they are different source.
Yeah, something else is on there, right? So that's good.
So I'll just put it down.
So, okay. And I guess I will come on stage to start the resolver after these two slides, right?
Sure.
That's probably easiest, yeah, right?
Yeah. So you can just, I don't know if everyone
Let's see, okay. I don't know either.
and resolve before the sponsors.
Yeah, exactly. Because that might take a while for them to get here, right? Yes. Even though you only hit them at the top, right? Only for the medals, I guess.
It's just for the top,
Yeah.
just for the medals.
Yeah.
I think it goes quickly. So I will tell Veronica that we are starting now.
Yeah. Yeah, exactly. I'll be on the second floor.
Yes.
I'm running when we start the revolver and then.
Yep, absolutely.
Okay.
So how much time do you want? Okay. So we have the Huawei here, and we need Andrei. So we start. Okay, so I will start with the quest. We have Huawei, but do we have Andrei from JetBrains?
I already sent a message to Veronica.
Yeah.
Let's see if we
still need a 15 minutes because somebody expected to start. Ještě zavoláme všech těch 10, co tam se baví. Já jim poslal e-mail a nefotografa. Máme. Perfect. Takže jim prostě přidáme celý. Mají tam triko od Pinelli. Řekl mi Pinelli, že pokud by jim seděla velikost, můžu si ho nastavit vyměnit, tak je to nějak můžu zkusit říct. Jo.
Dáme ještě pár minut. You want me to start? All right. All right, hello everyone. We will start slightly earlier, so I hope that anyone who is from the outside can just jump in. And if you are on a live stream and you are watching us from somewhere else, you probably want to come down and join us. And we will start with just a warm-up, right? We will have the resolver of how the results actually ended up, but there was side competition going on as well. and many of you participated in a quest. I will ask my colleagues over there if they could switch to this source. So we had 37 participants who were assigned 18 tasks, which we will see in a second once the slides turn in, and this doesn't seem like the right space. Oh, it probably does. It just has the wrong sharing, right? So let's see if we do. It will just take a second, but we had 37 participants in 18 tasks that were given to you by the quest. We had 320 submissions, and we have 10 people to award. And before we get into that, one fun, here we go. All right. Well, I will keep that fun story for a later time. And I might share it, I might not share it, because there was a last-minute submission, last-second submission that was after the deadline, and it would totally change everything. All right, so these are the numbers that we had for a quest, and I would like to invite the 10 of the names that we will have on the slides to please come on a stage, and you will receive a special award, and I will ask Mr. Photographer if he could also take the picture. So if you see your name, please don't be shy, come on the stage. We would like to recognize you here and give you a little award. And as they are coming in, I would like to recognize Vašek, who puts it together. So thank you, Vašek, for making a social event. I see 1, 2, 3, 4, 5, 6. So we are still missing 4 people. He's not here. He already took off. So we have 1 minus. What 11 count? 11 space. Well, I can only take the 10. And if your colleague is not here, you could still take his prize. Is that right? Would you like to be his proxy? Do you know the design pattern proxy? Or surrogate? Awesome, come on stage. And all right, so who do we have here, guys? I didn't read the names. Or who is missing? After we take picture, Mr. Photographer, I would like to make sure that we have at least someone who could proxy the prizes to the missing 4. So we have 1. If you know some of the name that is not here, please come to Vašek and he will later give you the awards. So thank you guys for engaging. I hope you made some social connections with your friends as well. And trust me, it's the biggest win from this competition, the social connections. So thank you again and give them a hand. Just an announcement, you can go down. There is a t-shirt. In case the t-shirt wouldn't fit, go later on to the Pinelli and they will adjust the size as you need one. I think the winner just arrived. Oh, 1 winner arrived. So you can pick up your prize, your award, but you missed the top picture here. All right. That makes us move into the resolver. And Nikki, if we can make it run. All right. Understand. So we will be resolving and we will be recognizing various levels of honors. But when we come into the place where we are recognizing the awards, if you are the team, please proceed to the stage through the side on your left, on my right side. So where you see the photographer in black, that would be the way to get on a stage. I want to say one thing. You might be perfect, you might not have had your day, but you are already the top teams from your countries most of the time. There are some countries that are represented by many teams, but even if it was not your top day, you are already here and you participated in the European Championship. And that's a great recognition. And if I could, let's give a hand to everyone who participated in a contest. So let me remind you something. we have 16 teams that can promote to the World Finals. You probably know, because you went through the regionals, that 3 teams already qualified for the World Finals from the regionals. But we have 4 more to give in this contest. That means if you qualified already, you cannot qualify today. But those that did very well today can qualify to the World Finals. And one of you, one of the teams, will receive one of those cups. You see different sizes, right? To avoid a confusion, this bigger cup already has the winner from 2024 Prague. So this cup is not going to be given to your team. This cup will remain here, and it will travel to Warsaw because they are the 2026 EUC. And to make it even more fun, there is already a name of one team that won in Prague, the University of Warsaw. Big hand to University of Warsaw for hosting the next EUC and winning the last EUC. So the smaller clone of the bigger cup will be awarded to the champion from the Europe contest. And we are to find out which team it is, and maybe we will be surprised to the last moment because we got the status of the scoreboard frozen 1 hour before the contest got over. Are you ready to start with the resolving? Yes. So maybe to know that this kind of resolver is available to you at any contest. So if you do even the local contest, you can just reach out to one of those names. Or I have Nikki here. Nikki, just raise your hand. That's the guy to talk to. And this resolver can be used at any contest. That's a very nice tool, right? So here we were before it got frozen. So what do we see here? We see tiles, right? The green tile, it was accepted. To remind everyone, the first number is the attempt, the second number is the time. And if you do the sum of the times is the score, the score on the right side. So the winner has the highest number of solved problems and the smallest number of the aggregated time. If you do multiple submissions, the teams probably know, but I'm just reminding to the coaches and the audience here, right? So if you do the submission multiple times, your time multiplies. So it aggregates. That's kind of a penalty that we have there. But apart from the the green ones that are resolved, there are red ones that we didn't solve, but we at least attempted. And the blue ones are those that we are about to find out what happened. But we also see kind of dark green. It might get blended a little bit from the distance, but there is a green border. And these are the first to solve, and we recognize these as well. So when you will go to the registration system, there is a certificate that there will be a certificate that you could receive. All right, so let's go all the way down because we want to resolve bottom down rather than the other way around. So here we go. We have Comenius University 1 pending, 6 submissions. Something happened. One more click. Yay! Jumped up. We have Uzhgorod. Unfortunately, it's no. We have Universitat de Porto, and it's yes. Comenius. We are done with the submissions. Norwegian University of Science. It's no, and it's yes. École Normale Supérieure de Paris. First, and it's yes. We have a long name, Grenoble. It's no, and it stays there. University of Bucharest. First is no, and second is yes. We have University de Belgrade, and unfortunately it's no. We move up to University of Porto, but. We stopped here. Why did we stop here? Because they qualified to the World Finals from their regionals. All right, little over the 40 teams to resolve. So let's see what else do we have here. And we see there the Universitat de Porto. And it's no. Even we see another Norwegian occurrence, it's no. We see University of Bucharest, no more to resolve. École Normale Supérieure, yes! We have Chalmers University, first is no and second is yes! Technikon Israel Institute of Technology, and we stay here. Aarhus University, and we go up. Taras Shevchenko is yes. Vienna University of Technology, and it's no, we stay here. And we have Cyril and Metodeus Skopje, and it goes up. We have AGH University Science and Technology, and it's no, we stay here. Masaryk University, and it's yes. We have Politecnica de Catalunya, and it's yes. And one more pending, Middle East Technical University, and it's yes. Università degli Studi di Milan, and it's no and no. We stay here. University of Novi Sad, and it goes up. Aarhus University, and we stay here with a score the same as, well, the same as Cyril and Metodeus. All right, École Normale Supérieure, we stay. Taras Shevchenko, it's no, we stay here. Chalmers University, and that's the final. We have two more pending. The first is no, and the second is, it's no. Kharkiv National University of Radios and Technology, and we go up. University of Ljubljana, 12 submissions. It was no. Middle East Technology University, and we stay here. We have two more in Technische University Munich, and here we go. Politecnica Catalunya, and it's up! Masaryk University, here we stay, but we recognize there is slightly different color. I think that they received the first to solve problem J, so let's give them a hand. Congratulations again, and let's look back. All right, we have a plenty there. 33 up, right? So let's see how the Charles University did. They have 3 pending, and it's yes. École Polytechnique Fédérale de Lausanne, and it's yes. We have the Warsaw, the big guys, and it's yes. Sofia University, 2 pending. The first is yes. 11th attempts. Etves Lorat University, and it's yes. Alexander Jon Kuza University of Leassi. It's no, and it's yes. The Paris-Saclay University, and we are staying here. University of Novi Sad, no more to resolve, but we stopped here. That means that they qualified to the World Finals from their regional competition. Let's give them a hand. All right, so if you didn't see your team's university name, you are still in the game. And I think you are like, okay, just make it move. I want to see how did I do, right? Just make it move. All right, let's see what's next. So we have the University of Cambridge above us, and they have 1 more pending. All right, University of Cambridge. Will that be yes? And it was yes. Scuola Superiore di Studi Universitario de Perfezionamento Sanana, and it's yes. Tel Aviv University, then it's no, and it's yes. We have Vienna University, last minute submission, it was no. We have Union University, Faculty of Computer Science, yes. And we have University of Wrocław, and it's yes. Neapolis University, Paphos, and it's yes. 7th place. Hasso-Platter Institute, and it's yes. École Polytechnique, 2 more. No, 1 more. And it's yes. All right, what happened here? What happened? Do we have an error? Hey, someone help me, do we have an error? What's going on? What happened? Back in the system. Any other proposal? It's a feature. It's a feature. You're a computer scientist. It's always a feature. You never admit it's a bug, right? So if it could be a feature, what could it be? Reverse engineering, guys. What could it be? Oh, wow. Yeah. We have a 5 and 6 divider, right? So we have a honorable mention here. So, one more click. And let's give a hand to all those universities with a honorable mention. All right. Are we ready to continue? Yes. All right. What else do we see? We see one more pending from Kharkiv, and if they made it, they will jump up all these 6 solved problems, right? So look at all these guys that have the blue tiles. For them to make one more successful submission takes them to the upper tier of those that solved 7. So here we are in a big game, right? But let's be realist. If you see 5 pending submissions with time 299, is it yes or is it no? Yes, okay, let's get yes. Almost. So we have Politecnica Catalunya, here we stay, Sofia University, we stay, Technische Universität Munich, we stay, Charles University, 2, no, and no. Warsaw, that's where we are, but we stopped here. See you in World Finals. All right. You have 24 more to go, and at West Laurent University might make a jump. But we need to run, and we made the jump 8 times, and maybe the last jump is the jump. And it was not. École Polytechnique Fédérale Lausanne, and it was a big jump. École Normale Supérieure, it was no, but Oxford has 2 more. Oxford, no. We stopped here. So, Scuola Normale Supérieure, congratulations, you solved the first problem E. All right, so should I tell the story about the Oxford or no? You know, 42 versus 32, that one little constant there, but you changed it 17 seconds after the contest. Oh, you know what I'm talking about, right? So the first one is no, and the second one is no. Just little tiny constant. Well, we skipped EASU, we are in Bucharest, we have one more Bucharest, and we stay here. Tel Aviv, we stay here. Scola Superior de Supimi Universitate de Professione San Anna, we stay here. Latvia, we stay here. Cambridge, stay here. Faculty of Computer Science, Union University, it's no. But, we have one green that is a dark green. So, not only that, first to solve problem F, we also qualified from the regional. All right, how many more to resolve? How many more to resolve? We are close to the medals, we are close to the hot pool. So now we have those that were lucky today, or whatever we call it. University of Wrocław, you have one more pending there, right? University of Wrocław, did you succeed or did you not succeed, or you don't know? We will find out now. 10 submission and it's no! University of Tartu 1 and it's no. I have another bug. I know who to blame, that's him, right? All right, the highest honors, guys. Give a big hand to all the universities that are coming up. Again, I want to remind everyone, you did great. And you know that you are top in your country. And sometimes it's about luck, sometimes it's about the judges not preparing the solutions that you were really practicing for. Sometimes you did not have your day. But the life doesn't end, and we have another rounds coming up, and we all know that the next round is going to be in Warsaw, and Warsaw is extremely excited about it. So you should be excited about it as well. And you know what? If you don't qualify, you can still qualify as a coach. And trust me, we will be happy to accommodate you, welcome you, because this is all driven by volunteers. So we are very happy to be part of your family. And we see you as part of our family. So please don't be afraid to say, hey, I want to work with you guys. I can come up with better problems than you came up with, or I can make that event happy. I mean, better than I saw it, but this was a great event. Do you agree? And that was a great event because this guy and all the volunteers from the University of Porto. Can we give them one more hand? I know they got many times, but... All right, we are jumping to the big stage. We have 12 more to recognize. But I would like to say the following. Before we do so, we also have to recognize one thing. We have sponsors, and you know, these sponsors went above and beyond. And they are not running away, they stick with us. They have been here for many years, and we believe that they will be here, and why they are here? To support you guys. So, I would love to welcome a couple of names for the awarding ceremony. And Fernando is definitely one of those that should be at the award ceremony. And a part of that, I would like to invite a couple of other names. So for the bronze medalist, I would like to invite Jiang Kriu, the director of Warsaw Research Center for Huawei Poland. Please come on stage. Thank you. Please stand next to Fernando. And the second person I would like to invite is from JetBrains, Andrei Ivanov. And Andrei is the Senior Vice President of People and Research and Investments. But did you see that? Did you hear that? People, they care about people, right? So the important thing is we are happy for all the sponsors that are here. You enjoyed the dinner yesterday, but it wouldn't be possible without their support. And why they are here? Because they believe this is a good thing. So even if you didn't succeed today, don't run away. You are still part of our family. We are all learning and we are improving. All right. Enough talk, right? We want to see those guys. These are the big guys that were lucky today. So we have École Polytechnique, and it's obvious that there is not going to be any change. So please come on stage and let's hear their big name as they are coming up. École Polytechnique, please come on stage, this way. They qualified already to World Finals. They also were the first to solve problem A, and they solved 6 problems. All right, ready for the pictures? Mr. from Huawei, Mr. from JetBrains, we need you maybe here, one of you. And keep in mind that all the awards you can pick up later on at the booth. Congratulations, guys, congratulations. Thank you so much. And let's get into the 11th place, bronze medal. All right, we have here Universitat de Pisa, sorry. I was just so excited. And I came from America, and the Pizza Hut, you know, all the Italians that I bring in, they are like, oh, that's not pizza, this. Oh my God, you have cheese in there. All right. But we have a different problem to solve, right? They made 4 submissions, and their time is 2:97, so they were probably not too stressed. Do you agree with me? Guys, you're here, right? Did you solve it? Did you solve it? No? No! Are you sure? What's going on? One more. Unbelievable. Unbelievable, guys. Congratulations. All right, but we have to downgrade down, right? And see who got now pushed down. And who do we see at the spot number 11? We see there Saarland University, and they have 1 submission. 284. I sense some confidence from you guys, right? So did you make it happen? Yeah? Yeah? All right, all right. I heard yeah. And it's a dank. It's yeah. Holy moly. 2nd position now. I'm sorry, Delft, they pushed you to number 3, and we see maybe, well, we will get there, okay? So number 11, Neapolis University, Paphos, we have 1 submission, 259. Should I be optimistic here? Guys, are you here? Should I be optimistic? Yeah, okay, okay. I like that spirit, I like the optimism. And let's find out, let's. Oh my God, come on please, come to us, but we have maybe some surprising news for you guys. Maybe. Wow. You are going to the World Finals, and you are the first team that qualified from here. Congratulations. Just come in there, they will be around you. Wow. That's the first out of those 4 spots that go to the World Finals. You know how happy these guys are? Where is your coach, guys? Did your coach desert you? Oh, their coach is in Cyprus. Does anyone want to be their coach? Yeah. Look, guys, for the next year, they want already to coach you. Congratulations. That's a big thing. Thank you. Here we go. One more picture, please. And I see 1, 2, 3, 4, 5, photographer 6, 7. Wow. All right. We're good to go. But you are spotlighted today, guys. You qualified from here. I'm sure you're very happy, and we are looking forward to work with you. All right. What else do we see here? I see Hasso-Platter Institute. Hasso-Platter Institute, one submission, 269. You know, I was optimistic in the previous one, and they said, no. So, is it yes or is it no? No? I hear no here. Someone disagrees. All right, let's find out. Let's find out. Let's find out. That's the 10th position. 10th, bronze medal. And it's... Oh my God, I have to click space one more time. Yay! Wow! Hey, Delft University, you were second, now you're 4. I don't want to pick at you, but look at you. Yeah. All right, we need to resolve, right? And we see who is at the position number 10, and they are the first to solve, and they are also the team to be recognized. So please come on stage, and you already qualified to World Finals, but you did great job here. You did great job. Guys, this should give you confidence because you technically qualified twice. You qualified from the previous contest and you qualified from here as well. But with that confidence, you should not stop working. You need to work hard. And do you remember what we said 2 days ago and 1 day ago? We said that all the teams that qualified to the World Finals are also invited to the official camp in Poland, right? So you still have opportunity to practice and improve. So please don't stop learning, okay? Never stop learning. Be adaptive. Congratulations. Karlsruhe Institute of Technology. Wonderful. Thank you, guys. And I hope to see you many years upcoming to the stage, all right? That's the coach, right? That's the coach. All right, thank you, guys. All right, what do we see next? Zagreb has currently position number 9, right? And they have one more submission. 2 actually, right? The first one obviously didn't make it, but the time is 2:65. Zagreb, where are you? Zagreb, raise your hand. Okay, our compassion with you, whatever happens now, okay? I'm gonna show it, whatever happens. All right, Zagreb, we are there with you, we are there with you, and we are there with you. Wow. Wow. They pushed down some big guys there. All right, let's see. So what happens now? These guys have 2 more submissions, right? One is 264 and one is 299. So let's be realistic. The first one seems like maybe. The second one is like, oh, you would have to be really lucky. All right, but we are there with you at least for the first one, okay? Is it yes? Is it yes? Who wants yes for ETH Zurich to promote up? Who wants yes? Tell me now. Yay! Well, obviously their team, but what about the others? Be a little supportive. They are your family, okay? Like little brothers. Can you say yes, please? Yes! Okay, Zurich, it's yes, you have to do that, okay? Please do that. Otherwise, you did it, yeah. Wow! Wow! It's like no one wants to keep the 9th position. Is that right? Is my interpretation correct? But unfortunately, we have no more submissions in the 9th place. So, École Polytechnique Fédérale de Lausanne, first to solve problem... Which one? Problem C. 7 solved problems. And you qualified from here. You qualified from here. You are happy to be here today. Congratulations. École Polytechnique Fédérale de Lausanne, bronze medalist, and they solved 7 problems. That's a big thing, guys. Congratulations. École Polytechnique Fédérale de Lausanne, bronze medal, congratulations, promoted to World Finals. Guys, keep the spirit high, because there is one more competition to go and one big camp, or maybe 2 or 3 or 4. How many camps do we have here? How many camps? Like everyone wants to do camp now, so please be aware that you can go to all those camps and still improve. But in Baku, we want to see a good result. Just like you qualified here, you will do it in Baku. And come next year, okay? Thank you, guys. All right, that's outstanding. I am really impressed. Universidad de Pizza, do we still have? Oh my God. I apologize. I brought the 25% tariffs with me, and now I only think about the pizza that will increase the price in America, right? All right. So we still have bronze medals, right? We still have bronze medals. So please, guys, come on stage. We will recognize you, and you already qualified. But you would qualify from here again. Do I have you here, or did I mispronounce it too much that you just don't want to come on the stage? I apologize. This way, guys. So you were also first to solve the problem I. You solved 7 problems, and you did outstanding today. And you again proven to us that you did it twice. But where is your coach, guys? Oh, he's in Pisa eating pizza. I see. All right. Congratulations. Universidad de Pizza. Pisa. Oh my God, I will never make it right. You can always mispronounce my name. You know, I'm Tomáš, but in America they call me Dames. So that's fine. All right, it's better to call pizza than Dames, right? All right. Thank you, guys. Congratulations. All right, so what else do we have here? Are we done? Are we just done? No, not yet? Not yet, not yet. Someone is like, no, I want my prize. I want to see what's happening next. And you know, we have 2 gold medals, we have 3, 4 silver medals, and I see we have the last to award for the bronze medal. And I see Jagiellonian University of Krakow, and they don't want the bronze medal. They want the silver medal. And they made 5 submissions to the last moment. Okay, guys, we need a big spirit here, right? And they could push the Delft University of Technology down. You know, I will get back to you to give you some spirit later, but now the spotlight is Jagiellonian University in Krakow, depending how you pronounce it. All right, they have 1 more submission. Is it yes? Is it yes? Is it yes? I think it will be yes, so let's see, guys. No. All right, bronze medal is still good medal. Come please on stage. And you did great. You did great because you qualified technically twice. You qualified from certs, and you qualified from here. And second of all, you solved solved the problem K as first team. And you solved 7 problems. Wow. Coach, are you happy for your team? Are you happy? Awesome. Congratulations, Jagiellonian University in Krakow. Please take the pictures of our bronze medalist. Congratulations again. And see you in Baku. And see you at all these training camps that are taking place, okay? All right, thank you guys. And we will need to do a little swap. So let me invite on the stage for the silver medalist, Mr. Yang Ren, the director of Edinburgh Research Centre, Huawei. Thank you. And I was asked if we could add one person. Is Boba here? Boba! Come on stage. Boba, you were the last year director. Is my memory right? I think it's yes. Silence means yes. All right, all right. So, Delft University, number 6, 2 submissions. All right, now we are in a spotlight, right? A second ago I was making fun of you because Krakow could totally jump over you. But you have 2 submissions there. Wow, 12 submissions there and 2 submissions there. All right, where is the spirit? We all have to support each other, right? So it should be yes. I want to hear yes from you guys because Delft doesn't want a silver medal. Or do you want a silver medal? No, I heard no here. I heard no, 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 no. No, okay. So let's go. Let's go to C. Let's go to see the first one. Okay, Delft University and spotlight! Wow! 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 So now I was making fun of you the whole time. If you are the number 1, you will be making fun of me, right? But look, 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 there is also Utrecht. And there is Zurich. And they want you to go back below them, right? Okay. But what is obvious here, we know who the next guy is because there is no more submissions. So please, guys, from Saarland University, you are the first silver medal. Congratulations. Please come on stage. And you qualified from here, guys. You qualified from here. So you must be happy that you came for this weekend, because this weekend promoted you to World Finals. What a great investment of your free time. Congratulations, Saarland University. 7 solved problems and silver medalists. Outstanding, outstanding. Thank you again. Thank you. Congratulations. Great work. All right. Who else do we have here? I think it's kind of clear now for the next few guys. So please, Hasso-Platter Institute, come on stage. And we would like to recognize you for the silver medal. Congratulations, you qualified already from your region, and you qualified again. So you are overqualified. Outstanding. Congratulations again to the Hasso-Platter Institute. Outstanding. Thank you guys, and good luck in World Finals and all those camps that are piled up ahead of you. Zagreb, are you ready? I don't see more submissions, so please come on stage. We would like to recognize you. You already qualified from CERTs, so you are overqualified again. The University of Zagreb. Silver medal, 7 solved problems. You know, it's tight competitions because all these teams we see solved 7 problems so far. And then it's tiny detail, right? Like, oh, I made a human error and just counting twice. That's outstanding, guys, outstanding. Come closer, don't be shy. The University of Zagreb, congratulations. And coach, you did a great job. I watched you over the years, and it was steps by step by step, and you are really making it to the top. We are so proud of you. Happy to have you here, guys. Congratulations. All right. All right. Now the hard task. ETH Zurich. You don't want the silver medal, right? You want the gold medal. All right, the spotlight is on you. You have 2 submissions. You have two submissions of the same problem. And it's 299. And we saw this pattern before. But there is the light at the end of the tunnel, and we want to find out. So I would like support of every single soul in the room that this little blue box turns green. All right, are we ready? Yes, everyone is praying for their support? Yes, okay, guys, I need to hear it. They need to hear it, all right? They want to hear your support. That's silence. All right. That takes long. It must be back. But guys, we were there with you. You heard it, right? You heard it. We were there with you. We were there till the end. Come on stage. We want to recognize you. ETH Zurich, please come on stage. You already qualified, and not only that, you solved 2 problems as the first team. Wow! Congratulations. That's amazing, guys. ETH Zurich, our silver medalist. And please remember, guys, all these guys supported you there. You heard it, right? They were praying for you. So next year, you are there to support them as well. Congratulations, ETH Zurich team, silver medalists. Outstanding. Thank you, guys. Thank you. And we are here to recognize the gold medalist. And I would kindly ask for the gold medalist Jun Hu, the director of Paris Research Center Huawei France, to come on stage. Thank you. All right, and I see there Utrecht and Delft University. From which country are they? Oh, wow. Wow. We have 2 teams from Netherlands and the Dome Judge team. A lot of those guys are from Netherlands as well. And I was sitting there and it was loud. It was really loud. Congratulations to both of you. That's unbelievable. But we need to find the one champion. But you both will get a gold medal. And that is outstanding. So, Utrecht, we are with you here. You have submission to problem D and submission to problem K. And you can totally beat the Delft. Right? All right. I again want to hear the prayer, the collegiality, that you are spotlighted with Utrecht to actually take that first place. All right, are you with them? Sorry, Delft, you don't need to, but everyone else. Utrecht, Utrecht, Utrecht. Ah! We have one more chance, okay? One more. Problem K. Okay? Are we there? Are we ready? Utrecht, we want to see you go up. Utrecht! Ah! Come on stage, guys. It was great. What I want you to recognize, they qualified from here. They qualified from this contest. So what did they do? They went to the regional and they really liked it. And they were practicing outside of their class. They were practicing overnight. They were practicing over their weekends. And they were dedicated. And it paid off. Did I say the story right, guys? Oh, you didn't listen to me, right? Just say yes. Just say yes. All right. All right. Congratulations. University of Utrecht. Gold medal. Gold medal. That's outstanding, guys. No one will ever take this from you. That's an accomplishment. All right? That's outstanding. And the world finals are there waiting for you. And all those camps that are piled up. So you definitely want to go there because you want to beat the Delft University, right? In the next round. Yes! We are waiting for you. All right, thank you guys. Thank you. Outstanding. And I think we all know, we all do, there is one champion that we all are so proud of, but Delft, we see that blue tile there. All right, okay, Delft, did you do that? Be honest. No, no, but you tried. Oh yeah, I know, but we all would wish that it was there, but it might be there. They are just playing the game with us, right? And we want to show our collegiality, right? Because they are going to represent all of you guys in the World Finals, right? And we want this guy to beat everyone else. Is that right? No, we want them to be collegiate, support everyone else, but do better than them. All right, so is it yes? We need a big support because you see, they said 12 and 299. But we need to show them that we still believe in them, right? Because they are the European champion. Europe champion, I apologize. Europe champion. We want to hear yes. Say yes, please. Yes, yes, we all are with you guys. We all are with you. But we are realists, right? And it was, but I think you are still happy. Are you? Please come on stage. Unbelievable. Unbelievable. Delft University of Technology is the 25th champion of problem-solving, competitive programming in ICPC. Congratulations, guys. And you overqualified because you made it from your region, you made it from here, and you also were the first to solve the problem. Wow, look at that. You will hold the big one. First the photo, the big one, and then you get a small one, right? We know these tricks. We know these tricks. All right, so let's take a photo without it, and then we would like to see the emotions when you hold the trophy. All right, let's give them a big hand applause. Whoa! Woo-ha! Guys, as you hold it, look at the name. You see Warsaw University on the cup, and next year there will be your university on the cup. So you are writing a history. You wrote a chapter that no one will ever take away from your university. The small one you take home, but the big one you will keep, and we will show everyone that you made it. And that will stay here for years. Congratulations. Nadine, are you here? Could you join the team? And I told you the story that 2026 is Warsaw, right? And can you tell me the pattern? So Warsaw won last year, and that Warsaw is 2026. So 2027. But which country should it be at? All right, you heard it, guys. You heard it, you earned it, now you owe us. That's outstanding. Congratulations. We have high expectations now. And I want to remind everyone that you solved 8 problems. Right? They are the only team that solved 8 problems today. So they really earn it. Let's give them one big applause for that one extra problem they went. Way to go. Way to go. All right, thank you guys. Yeah, of course.
Can we just get a picture with the gold medalist / the Dutch group?
You want the judge room, so judges, please come here. Judges, all the judges, come on stage. They want your picture there as well. Because they defeated you, right? This is the team that defeated the judges. And if I may, Dome judges, come there as well. Dome judges, because you were a big support, you were just screaming the hell out of the room when they made it, and most of you are also Dutch. So please, Dome judges, you too, yeah, you. Dome judges, any other Dome judge here? No other Dome judge, please go there if you are in a room. You know what I tell to the winners? You will be the judges once you promote into the level that you cannot compete. So, I'm sorry, you earned it, guys, right? We all see you, we all witness that you did well. You will be great judges. You will create great problems. And we are here to solve them. These guys are here to solve them. Are we ready for the pictures, or did the camera guy also went there so we don't have anyone to take a picture? Oh, here we go. Here we go. Congratulations. Thank you, everyone. Thank you, judges. Thank you, DOM judges. Thank you, the organizers. Thank you, the sponsors. And would you, Veronica will share a little bit about the prizes.
Yes. Again, congratulations to everyone. Small reminder for all the medal teams, gold, silver, bronze. We have presents for you on behalf of the sponsors, Huawei, JetBrains, Jump Trading, Finally, and they are all waiting for you, and Vincent, of course, Bitcoin. So they are all waiting for you at their booth after the ceremony, during the dinner. So just don't forget to pick up your prize. And congratulations.
All right. And Fernando, I would like to have the pleasure for you to close it.
Yes, thank you. Well, what a day. I
think we all need to give him one more round.
Yes, thank you. So all the teams are to congratulate because it's not so easy to get to this stage. So by getting here, you are already winners, okay? So congratulations to all the teams, first of all. And second, I would like to thank the work that the judges did, because it's not, I know that it's quite a responsibility, and it gives a lot of work just to prepare a nice set of problems. So thank you very much. Please stand up just for another round of applause. Yes, thank you. Yeah, thank you. So, as you can imagine, organizing this event is a lot of work for many people, okay? So, we already acknowledged the judges. I would like also to acknowledge the work from the DOM judge team, from the ICPC Live, which are all the green shirts, okay? I think they did a great job because there was a live stream. I think the event was seen outside of the contest area all over the world and is due to you. Okay, thank you. And I would like also to thank all the systems and all the staff that some from our university, some from outside our university that worked both in systems, local organization, and the volunteers, of course. I would like them to stand up first, staff and volunteers. So let's acknowledge them. Thank you. So, my work and my job was much easier because of them, because they did the most, okay? But I would like to mention 3 ladies. Olga, Alexandra, Isabel. They were amazing. Thank you. Thank you. Of course, and Ricardo and Danielle that is over there, they also, and Leonardo, sorry, they helped a lot, and they said, Professor, you have to relax. We will do it. And they did it. Thank you very much. So, without further ado, this is not the end of EUC. We have 2 years ahead already decided. Tomasz already disclosed some information about the future. And it is my pleasure to invite the Warsaw leading team for EUC 2026. Jan Madej, please. And Rafael, yes. Thank you very much for having your bid. Yes. So, Danielle, please, can you put the video? Audio, please, as well.
Welcome to Poland, a country with a rich history, a modern spirit, and incredible energy. Warsaw, the host of the ICPC Europe Championship 2026, is the heart of Poland and one of the most fascinating cities in Europe. Warsaw is perfectly connected to the whole of Europe. Every day, Warsaw's airports handle up to 80,000 passengers. It is also among the tallest cities in Europe. Only Moscow, London, and Frankfurt boast more skyscrapers. The symbol of Warsaw is the mermaid, whose statue stands in the vibrant Old Town, a UNESCO World Heritage Site.
I'm sure that you will enjoy your stay in Poland, especially in Warsaw, and you will have fun both competing and also seeing the beautiful city.
Just a short walk from this historic district is the main campus of the University of Warsaw, the host of the ICPC Europe Championship 2026. The University of Warsaw is one of the top universities in Central and Eastern Europe. With over 200 years of tradition, it boasts an impressive list of distinguished alumni, including Frédéric Chopin and Nobel Prize winners. The university is known for its modern campuses, innovative laboratories, and green gardens. With more than 100 study programs, it educates future scientists, engineers, and technology leaders. The jewel of the University of Warsaw is the Faculty of Mathematics, Informatics, and Mechanics, which has been training world-class programmers for years. For over 30 years, teams from the University of Warsaw have continuously qualified for the ICPC World Finals. They have won the World Championship twice, in 2003 and 2007, and secured the runner-up title twice. They also hold the title of the first ever academic European champions. In 2024, the University of Warsaw team won gold at the ICPC European Championship in Prague. Thanks to its talented alumni, Poland has become one of the world's key hubs for computer science. Our programmers receive prestigious awards and develop groundbreaking technologies. Jakub Pachocki, an expert in artificial intelligence, co-creator of the O1 model and chief scientist at OpenAI. Tomasz Czajka developed navigation and guidance software for crewed space missions. The University of Warsaw is not only a leader in programming education, but also an active member of the ICPC family. It regularly hosts the world's top programmers, offering excellent infrastructure and unforgettable experiences. The competitions take place at the Faculty of Management of the University of Warsaw with the support of the organizational partner, Foundation of the IT Development.
We had the pleasure of hosting World Finals in 2012, we had the pleasure of hosting Central European Contest, Polish National Contest. Now it's time for Europe.
We are ready for the next challenge. See you in Warsaw in 2026.
We are missing one very important person here. Krzysztof Dix couldn't come because of health problems, and he will be the director of the event next year. And we're coaching together for, well, about 25, 30 years, so pretty long time. I'm very happy that we'll organize this event. As you have seen, we did the World Finals in 2012, and I hope we'll be able to do as good as you did. Thank you very much, and the same, Boba, to you. Where are you, Boba? Thank you for the last event in Prague. So, well, you are very welcome to visit us, to come to us, and we hope we'll enjoy the time. Thank you.
Thank you. Can you say something?
Only one word. I would like to invite you to Warsaw. We try to do our best to feel as here a part of ICPC family. We are all part of ICPC family always. After you graduate, after you will be coaches, please feel free if you want to stay a few days before in Warsaw. We are always welcome to visit us. See you in Warsaw next year.
Thank you, Ian and Rafał. I'm sure it will be a good event, as good as this or even better, I'm sure. And we are looking forward to it. This is the closing of this event, but we still have the dinner upstairs, so please do not forget if you want to have dinner before going, okay? Many thanks for everything. I hope you enjoyed it, this championship, as much as we did, and I hope you still have time to enjoy the city. Thank you very much.
I'm sorry. I think this ceremony would not complete without a huge thank you for people who brought us all together. I would like again to call Boba Mamnova on stage, because without her, the ICPC may not be as prosperous in Europe as it is now. So a big round of applause to Boba. And of course, the director of this event, without whom we would not be in this beautiful city of Portland, University of Portland, of course, all the team, but special thanks and huge round of applause to Fernando. Without those two people who have the capacity to bring all of us together, we would not be here. So thank you very much, and let's get it a better event every year.
Thank you, for sure.
Thank you for coming, and we have to be thankful that we are European.
Yes.
So dinner is upstairs, okay?
Dinner is upstairs.
And also the prizes.
And the prizes are upstairs.